In the last separations video, I introduced a single-stage batch distillation process, aka the Rayleigh still, and I derived the formulas for the two material balances. And I left that video off by saying that there are 6 variables between these two material balance equations, and typically in any given problem, we would know what 3 of those are, or 3 values would be given, leaving us with 3 unknown variables left. And with only 2 equations to solve for those 3 unknowns, it would be impossible unless we had a third equation. That third equation is called the Rayleigh equation. And this video will cover the derivation of that Rayleigh equation. And in order to do so, again, I have to recognize that I did not write all the variables on my process flow diagram. I still have a flow rate of vapor going up to the condenser and the composition of that vapor. So I'm going to use those 2 variables in defining 2 other balances that I can write. So the other 2 balances are more conventional differential type of balances in which I'm balancing just the material that is in the reboiler. So write differential material balances, and I'm using the terms differential and integral material balances. I don't typically talk about the differences between these in material and energy balances, but they're in the book. So a differential balance is a regular material balance that we're used to, while an integral material balance is balancing 2 points in time. So a differential material balance is a typical material balance where we are balancing, we assume things are in steady state. So it's input plus generation minus output minus consumption is equal to accumulation. While integral material balances is more like a final minus initial type of balance. So writing differential material balances around the reboiler. And doing so is going to introduce these other 2 unknown variables, v dot and y, into our analysis, but we'll see how they're going to reduce in the end. So on the reboiler, I can do an overall material balance on the reboiler. So it is of the form, remember, in plus gen minus out minus consumption. The famous formula from MEB is equal to accumulation. And I don't have any generation or consumption terms because I have no reaction. And I also don't have any input terms because nothing is going into the reboiler at any time. Right? So if I draw a border around this process, I have no input streams going into the reboiler. I do, however, have an output term and I have an accumulation term because this is not steady state. So I'm left with output is equal to accumulation. And if I think about what that output actually is, that output is going to be V dot, right? So this is the expression for what is coming out of the reboiler at any time t. And it has to be negative because it's minus output is equal to accumulation. And the way that I write accumulation is similar to MEB. It is a differential term. So it's dB. I mixed up my notation for a moment. dB of t by dt. All right, so once again, this says that the output from the reboiler is equal to the accumulation of the reboiler, which is going to be negative because stuff is leaving the reboiler. I can do a similar balance for component A. So remember, this is overall material. I could do a component A material balance in the same fashion. So it's just minus V dot times Y is equal to D and then XB times B. And both of these are functions of time. I've been sloppy about making sure to keep those, but just in case, I'll write them both here. So this is dxb of t and dB of t by dt. And now we have 2 differential equations that we can rearrange in order to solve. So I'll start the analysis by looking at the component A material balance and recognizing that we can do I call it the chain rule, but I learned calculus in a weird way, or my calculus teacher had the rules mixed up. So I've been informed by students that this is actually the product rule, where you keep one variable constant and you take it out of the derivative term, and then you take the other derivative. So this right-hand side, so minus v dot times y is equal to xb dB dt plus b dxb dt. And then what I can do is I can substitute my overall material balance. So I can substitute minus v dot in for dB dt. Actually, scratch that. I want to do the reverse. I want to plug in dB dt in for minus v. So same thing. Right? I'm just choosing to plug in the different variable. So here it'd be y times dB dt. Substituting again, minus v dot is dB dt is equal to xb dB dt plus b times dxb dt. And now I have a dt term in every term of this equation, right? So this is a bit of shady calculus. This is not how differential calculus works, but you can think of it as like you're canceling out the dt. Or in other words, it's independent of time. So the next step is realizing that I have a common dB term, so I can group terms. So I'm going to bring this xb over to the other side to get y minus xb times dB is equal to b dxb. And now I have what looks like a differential equation right before I integrate it. So I can integrate both sides. Actually, hold that thought. I cannot integrate yet. I have to group terms before I can integrate. So I have a b on the left-hand side and on the right-hand side. I need to get those on the same side. So I'm going to cross divide through. So I'm dividing both terms through. So this step looks like 1 over b dB is equal to 1 over y minus xb dxb. And now I can integrate. And I'm integrating from time is equal to 0 to whatever time t. Even though time is not in the expression, right? I know what these values are at time 0. So at time 0, b is equal to f, and xb is equal to xf. And then this is also poor calculus form to have the variable of integration equal to the variable that you're integrating over, but I'm going to do it now just for clarity purposes. All right, but just keep in mind that in calculus class, you'd never see that. The integral of 1 over b dB is going to be ln. And if I take the limits of integration, it is going to be ln of b over f. And that is equal to the integral. Now notice I cannot integrate this yet. And that is because I don't know, y is a function of xb, but I don't quite know because I haven't described what the variables are yet. 1 over 1 over y minus xb dxb. So let's look back in the diagram and remember what even the variable names y and xb are. Remember, xb is my composition of the more volatile component in the reboiler at any time, and y is the composition of the vapor that is leaving the reboiler. So the relationship between y and xb are that they are in equilibrium. Y and xb are in equilibrium for all times t. So the integration of this formula is going to depend on how I can relate y and xb. So if it's the alpha relationship, I have a formula for that. I can analytically find what this integral is. Are in equilibrium with one another for all times t. All right, so let's just go through the possibilities. The first possibility we haven't really seen yet, but it is possible if you are looking at a very specific portion of the equilibrium curve. You can assume that y is in a linear relationship with xb. So again, if you have a linear form, then you would just simply plug in k times xb for xb, and you would compute the integral like so. The integral of 1 over, and the xb would factor out, k minus 1 dxb would be equal to 1 over k minus 1. So that would get factored out because the k would be a constant value. And I'd be left with ln of xb over xf. And then obviously that would be equal to the ln of b over f because that's on the right-hand side. Now, again, it's very unlikely that y is equal to k times xb. So there's another possibility that we can write. So if y is equal to alpha xb over 1 plus alpha minus 1 xb. So this is the equilibrium relationship that we've seen for most of the term. You recognize if I plug this whole expression in to y, I'm going to have a very complicated integral. So you don't have to know how to take this integral. I'm not actually going to plug it in. I'm just going to tell you what the value ends up being. So the integral, well, actually, I'm going to plug it in just for clarity's sake. 1 over alpha xb over 1 plus alpha minus 1 xb minus xb dxb. So again, I'm skipping a lot of algebraic steps here. And I actually have not tried to do this by hand. That looks like a pretty challenging integration. You need to break out your integral tables. That's ln of f is equal to f over w equals 1 over alpha minus 1 parentheses ln of. Okay, sorry about that. I had to check my notes really closely because sometimes I write this equation wrong and it causes confusion. I'm pretty sure that this is the correct form of this integration. So once again, don't worry about the steps of how to actually perform this integration. It's enough to just use this equation, knowing that it comes from the integration of this expression. And if you know what alpha is, and once again, if you know what 3 out of the 4 unknown variables are, this would then be the form of your third equation. So this is probably the most common form of the Rayleigh equation that you will see. One more possibility that we have to account for, and that is if there is no form of the relative volatility that accurately represents equilibrium data. So if there is no analytical expression, for y is a function of x. So let's assume that it's a system like methanol water, ethanol water, one of those weird ones where there is no constant relative volatility and the equilibrium curve kind of looks a little weird, kind of like that. There is no equation that I can use, so how can I go about integrating it? If this is the case, you'll want to use a numerical integration technique. One that I really like is Simpson's rule, which is pretty accurate. Use numerical integration technique, e.g. Simpson's rule. In the general sense, this is what Simpson's rule says. It says that the definite integral of some function f of x dx from an interval from a to b is equal to the range b minus a of the independent variable over 6 times the quantity of the value of the function at the one endpoint plus 4 times the value of the function at the midpoint plus the value of the function at the other midpoint. So applied to my equation, so if you apply it to the Rayleigh equation from xf to xb of 1 minus y minus xb dxb, Simpson's rule applied would then be the bounds of integration, so xb minus xf. And this would in general be a negative number, so don't be confused by that. xb is going to be less than xf because these are both of the more volatile component. The value of the function at a is going to be whatever y is at xf, right? So it's 1 over y of y at xf minus xb. So if I have a table or a graph of my equilibrium data, I would see whatever my xf is. I'm going to put it a little bit further this way. Let's say xf is there. The value of y at xf would be wherever on my equilibrium curve that value crosses, plus 4 times the value of the function at the midpoint. So I have to know what xb is then. So let's say xb is there. xb plus xf divided by 2 would be halfway in the middle. Right, so right there. And this would be the value of the function there. So 4 times 1 minus y at the midpoint, which is written as xf plus xb over 2 minus xb, and then plus 1 over the value of the function at the other endpoint. So it is y at xb minus xb. And crazily enough, Simpson's rule is actually pretty accurate for a lot of integrals. So this is a way that you could numerically integrate if you had, like I said, a function that could not be accurately described by a value of constant relative volatility. That will do it for this video. Last video for today, I have an example problem ready to go. See you there.